I'm going to record several problems involving limit laws and how to find the limit using the limit laws. So I've picked just a random selection of problems from the homework, hoping that each one of these will demonstrate a technique, and then through that technique you can expand and solve other homework problems. So let's take a look at question number 9. Okay. Question number 9 says we want to find the limit as x approaches 5 of x squared minus 6x plus 5 divided by x minus 5. Okay. So we begin with a problem where, now just off to the side here, let's write down our techniques for finding limits, right? What are our steps? What are the steps that they suggest we go through to evaluate a limit? So the first step, I call it the just plug it in step. In other words, the first thing we're going to try to do is plug in A. Now, if when we plug in A, we get an answer. Now, an answer is a number, a real number. It's not something that's undefined. If we plug in 5 and we get a number over here, we're done with the problem. Now, unfortunately for us, when we plug in 5, we get 25 minus 30, which is negative 5, plus 5. So when we plug in 5, we get 0 on the top. Now, a numerator of 0 is not a problem. A numerator of 0 could indeed lead us to an answer of 0. But unfortunately, in this case, when we plug 5 in the denominator, we also get a 0. So this is not a number. So the just plug it in step has not led us to an answer. Okay. From here, our second step becomes algebraic manipulation. Now, what do we mean by that? Well, there's various things we can do to the problem we've been given algebraically. First of all, we could try to factor and cancel. Perhaps if we factor the numerator, we're going to come up to a term that's x minus 5, or sorry, a factor that's x minus 5, and we'd be able to cancel this x minus 5, which is causing the 0 in the denominator, with the x minus 5 on the top, and we would be able to eliminate our problem. Now, another technique under algebraic manipulation, and we'll do a problem that involves this, is rationalization. We might want to rationalize the denominator, we might want to rationalize the numerator. It just depends on what we need to rationalize. Okay, so we'll stop here with our steps, because right now we've gone far enough to solve this problem, because while the answer is not 0 divided by 0, remember, if we just plug it in and we get a number, we're done. If we do not get a number, we have to continue doing our steps. Now, if we rewrite this, right, this is the limit as x approaches 5, we can factor the numerator, can't we? This is going to be x minus 1 times x minus 5 divided by x minus 5. It's just using our factoring techniques. Now, here we come to a point in an algebra class, we would just cancel the x minus 5s and the x minus 5s. With no further thought, we would just cancel. We would say something advanced as an algebra student, like, well, x minus 5 divided by x minus 5 is 1, so I can cancel that. In a calculus class, we need to take that just a little bit further. Oh, we're going to cancel x minus 5 and x minus 5. And we're going to cancel x minus 5 divided by x minus 5, because indeed x minus 5 divided by x minus 5 is going to be 1. But in the case of a calculus class, when we're working with limits, we have to pay attention to y is x minus 5 divided by x minus 5, 1, right? Just as a little thought over here, x minus 5 divided by x minus 5 equals 1 only if x does not equal 5. Because if x does equal 5, that's 0 divided by 0, and we know 0 divided by 0 is not 1. So we have to be able to look at this problem and guarantee ourselves that x minus 5 divided by x minus 5 is indeed 1. And the way we do that in a calculus class is we realize this means x approaches 5, but never reaches 5. And because of that fact, we know x minus 5 divided by x minus 5 is 1. We can then cancel x minus 5 with x minus 5. We can rewrite this as the limit as x approaches 5, and now we just have x minus 1. We can now plug in 5. This is a polynomial. We have the direct substitution property that says when you take the limit of a polynomial, the limit of a polynomial is the value of the polynomial evaluated at a. So we're going to, in essence, plug in 5 here. That's what we mean by just plug it in, right? That's not the technical term of what we're doing. And we're going to get 5 minus 1, and our answer is going to be 4, which clearly is not 0 divided by 0. So this is a very common limit problem we encounter in a calculus class. And it's often the case that we can move from this situation, which is not our answer, especially when we look in the back of the book and we realize that's not what they listed as the solution or the answer. We can move from there to the real answer by realizing we have to manipulate this algebraically. So that's a very common technique, okay? On the list over here, right? On the list over here, we have factor and cancel, we have rationalization. You could add to this common denominators. And I'm now going to do a problem involving rationalization, and then I'll do an example of a problem involving common denominators as well. I'll go ahead and leave this up. I think we're going to have room here. So let's grab a problem that would involve rationalization, right? So we could have something that's given to us like number 18 here, where it says the limit is h approaches 0, and we have the square root of 1 plus h minus 1 divided by h. Once again, we're going to start with just plugging it in. We ended by just plugging it in here. We go down the list and we always cycle back to just plug it in. That's our ultimate goal, is to just plug it in. But often, as I said previously, often to do that, we have to simplify first. And this is how we're going to simplify. When we look at this problem, if we try to just plug it in, we clearly have a 0 on the bottom. H goes to 0. This is h. That's a poly. I can plug this in. When I try to plug it into the numerator, though, I get the square root of 1 minus 1. I get 0 divided by 0 again. Now remember, our limit laws say you can take the limit of a quotient by taking the limit of the numerator divided by the limit of the denominator, but it also very explicitly states, that limit law very explicitly states, the limit of the denominator can't be 0. So that limit law is not applicable here. The limit law that says the limit as x approaches a of f divided by g is equal to the limit as x approaches a of f divided by the limit as x approaches a, that's a g. We'll fix that. The law that says this is equivalent to this has a very firm condition, right? It says the limit as x approaches a of g cannot be 0. Well, that law, therefore, does not apply to this problem because our denominator is absolutely 0. So where do we go from here? We could go to factor and cancel, but we don't have anything here to factor. So we could move to rationalization. What does rationalization mean? It means the same thing it meant in an Algebra 2 class. We're going to rewrite this, right? Make sure that you rewrite the limit on every step. Until you actually take the limit, you have to keep writing this down. So I have the limit. I have the square root. I have 1 plus h minus 1 divided by h times. Now I'm going to multiply this. I'm going to multiply it by the conjugate of this. I'm going to multiply by the square root of 1 plus h plus 1. Now obviously, if I multiply the numerator, I also have to multiply the denominator by the same thing. Once again, if we take a quick look at what we're multiplying by, we're multiplying by 1. Because if I put 0 here, I get the square root of 1 plus 1, that's 2 in the numerator. If I put the 0 here, I get the square root of 1 plus 1, that's 2 divided by 2, that's 1. I can, the rules of algebra allow me to multiply by 1. So what is this going to look like when we multiply? Right? What is it going to look like when we ultimately do the multiplication? Well, we're going to get the limit as h approaches 0. My numerator is the difference of two squares, right? I'm going to take this times this. That's going to give me 1 plus h. My middle terms are going to fall out because of the difference of two squares. Negative 1 times positive 1 is going to be minus 1. There's my numerator. My denominator now, if I rewrite it, is going to be h times the square root of 1 plus h plus 1. Now I'm going to take a quick moment here to talk about this denominator. A lot of my students, when they first start a calculus class, they want to do the distributive property down here. Okay? And I understand why. You're used to, in an algebra situation, if I have a distributive property possibility, I like to do the distributive property. However, in a calculus class, we have to be a little more cautious. We have to ask ourselves, way back here, and I'm sorry it's a little hard to see, I'll get a green pen to circle it with. Way back here, what was the problem with our question? Our original question had an issue, right? Our original issue was there was an h in the denominator which caused a 0 to be in our denominator when we just plug it in. What are we going to do to fix that? Right? What are we going to do to fix that? Well, what we're going to do to fix that is hopefully cancel that h with an h in the numerator. We ultimately want to have h divided by h, very similar to what we had here with the x minus 5 divided by the x minus 5. And we want to cancel the h's, because once again, we know h does not equal 0. That is our goal. So knowing our goal before we begin would lead one to not do the distributive property here, because the h is sitting outside this quantity and it's ready to be canceled with perhaps an h that's going to appear in the numerator. Okay. And if we simplify the numerator, right, we get the limit as h approaches 0. Again, we have to write this every time. The numerator turns out to be h divided by, and now my denominator is h times the quantity, the square root of 1 plus h plus 1. Okay. And now, because, the same reason here, because in this case, we're taking the limit as h goes to 0, and we know h approaches 0 but never reaches 0, we can cancel these. And our problem has gone away. Not our problem is in the question they asked us to do in the book, but the issue with the problem they gave us in the book. I now have a 1 in the numerator. My denominator is now the square root of 1 plus h plus 1, and we can just plug it in. When we do just plug it in, the limit of the constant is the constant. Here, of course, I get 1 plus 0, that's 1. Square root of 1 is 1. I get 1 plus 1, and I get 2, and that's the answer in the back of the book. Okay, so once again, 0 divided by 0, not the answer to our problem. The just plug it in step does not work unless we get a number. So I'll do another problem here. I'm going to have to erase the whiteboard. So I'll leave the steps out. We'll get these steps, these problems. another example from the book where we would have to find a common denominator. Something like 19, for example. 19 says the limit as x approaches -4. And now everything I'm doing over here, sorry not to interrupt, don't mean to be distracting here, but everything we're doing over here works with one-sided limits as well, okay? The limit as x approaches -4, and we have 1/4 plus 1 over x, all divided by 4 plus x. Here we sit, we're always going to try to just plug it in. Do not be afraid of just plugging it in. Every now and then, especially on an exam, professors love to stick a just plug it in problem down there in the middle of the test just to see if you're going to do all these steps when you didn't have to do them in the first place. We're kind of devious like that. So if I put -4 here, I get -1/4 plus 1/4. Well, that's going to be 0. Again, third time, 0 in the numerator is not a problem. I'm not worried about that. That doesn't cause me to have any anxiety. However, when I put -4 here, I get 4 minus 4. I get 0 in the bottom. That does cause anxiety. I know I have more work to do. I look at the problem and I ask myself, can I factor? No. Can I rationalize? There are no radicals. I'll try a common denominator. Where we ultimately want to arrive is to the point when we look at a problem, we ask ourselves a simple question. What would I do if I was an algebra student working on this problem? You get a common denominator. Okay, there you go. That's what a calculus kid's going to do. So where am I going to go from here? I'm going to rewrite this as the limit as x approaches -4. I'm going to get a common denominator. The common denominator on the top is going to be 4x, right? 4 goes into 4x, x times 1 is x, that goes here. X goes into 4x, 4 times, that times 1 is 4, that goes here, and I have this. Now, if I plug in -1/4, I'm not going to have an answer. I haven't done any simplification. All I've done is I've gotten a common denominator. Now, we know that this is a complex fraction. You have a fraction in the top, you have a fraction in the bottom. So we can rewrite this as the limit as x approaches -4. And when I rewrite this, we know the rules for solving a complex fraction. We rewrite the numerator, and we multiply by the reciprocal of the denominator. And we find ourselves in a situation very similar to what we found ourselves in the previous two problems. We have a quantity in the numerator that is not 0 because x only approaches -4, so that's not 0. This is not 0, so this divided by this is 1. And when I rewrite this, I'm going to be able to jump up to my just plug it in step and get an answer. When I plug in -4 here, this is a quotient. The limit of a quotient is a quotient of the limits, assuming the quotient of the denominator does not equal 0. That's our limit law. So when I plug it in, I take the limit of the numerator, that's 1 because it's a constant. This is a Pauli. I put in -4. The limit of a Pauli is the Pauli evaluated at the value of a. So I put in -4 and I get -1/16. And we're done. So this is what we are going to do to evaluate limits. Okay? These are the steps we're going to utilize when we're faced with a computational can you find the limit problem. And these aren't going away, right? I understand this is chapter 2, but limits are part of our lives now. They're going to be part of what we do. Limits are like negatives, right? There was a day that you didn't know there were negative numbers, and then there was a day you learned there were negative numbers. And on the day you learned there were negative numbers, well, from that day to today, they've never gone away. Limits aren't going to go away. Right? They're not one of those things we can say, well, I'll just kind of fake my way through the limit and it'll eventually go away. That's not going to happen. So the sooner we master our limit laws, the sooner we master these steps. One thing we can add here, right? I don't have any problems that that we are going to utilize in this video. But also under algebraic manipulation, we can put down trig substitution. That's where all those trig identities they taught us in pre-calculus come into play. And we can use those trig identities and we can change the value of what we have. Okay? So this is how we take limits. The last and ultimate technique is the squeeze theorem. None of us want to use the squeeze theorem. The squeeze theorem is arduous to use. We would much prefer to use one of these approaches up here to find limits. And in reality, most of the questions we're going to ask you to do that involve the squeeze theorem are going to clearly indicate use the squeeze theorem to solve this problem. And on top of that, more often than not, we're going to give you the two functions that you must utilize to squeeze the given function and therefore find its limit. Because it's the discovery of the two functions, the lower bound and the upper bound, that proves to be quite arduous when you're trying to use the squeeze theorem. Hence the reason most of us avoid the squeeze theorem. So I hope this video helps you. It shows you some computational techniques that you can utilize when you're calculating limits using the limit.